Welcome back. So in our fourth module, we were talking about the contextually constrained deep learning, where essentially not only we want to maximize performance, but also we want to make sure that an additional context is which leads to, let's say, constraint is satisfied. So we talked about privacy, we talked about memorization, and today we are going to talk about robustness. And later on, we're going to see how we can sort of systematically leverage additional context as constraint into our learning problem. Okay, and the reason that I'm mentioning robustness here is due to its intimate connection to privacy as well as memorization, thanks to this perspective, sensitivity perspective that we've talked about in previous lectures. And this is something that I'm going to also talk a little bit more in this lecture, and hopefully also connected to the context we talked about in previous lectures. So what's the motivation? The motivation is that the models that we're going to train, the deep learning models we're going to train, are going to be used in diverse scenarios where the conditions or the assumptions that we made when we were training the model are not necessarily met. Okay? So for instance, the type of the data that we're going to deal with at inference are not as nice and clean as the ones that we have dealt with during the training process. Okay, so therefore they have to sort of be robust or resilient with respect to, for instance, changes in the test data compared to the training data. Okay, and these changes could be due to various reasons, right? For instance, maybe the model is going to be used in potentially contested environment or environments where adversaries exist. So the change could be due to malicious activities. Now, if we want our model to be reliable, it has to be sort of robust or resilient with respect to these adversarial changes. A change could also be due to the existence of out-of-domain samples or out-of-distribution samples. So what that means is that the type of the test samples that we're going to deal with are slightly different or somewhat different than the type of the samples we have seen in our training data. Okay? So to keep it simple, for instance, maybe in the training data, the model has only seen for instance, black and white cats, the images of black and white cats. But at test time, it's only going to see the images of gray cats. Okay, so this is an instance of out-of-domain sample or out-of-distribution sample. Okay, so therefore our motivation is to make sure that when we train our deep learning models, we sort of account for the fact that there could be changes in the data or changes in the distribution of the data. Okay, and by doing so, we want to basically introduce some notion of robustness or resilience into our training process. Okay, and this is important because if you don't do so, the model could perform quite badly. So if you recall, this is an example we talked about before in the context of zero-order estimation, where one motivation for that was, again, adversarial robustness or adversarial attacks. And there we discussed that there are scenarios where, for instance, a fully trained model that is highly confident on a specific image, for instance, an image of a panda, is not going to perform well if we introduce some small perturbation, some small noise here to our image. So in this example, instead of predicting the label to be panda with somewhat significant confidence, it's going to predict it to be gibbon, another animal, with a significantly large confidence. So the model is going to be confidently incorrect. Okay? So we want to basically make sure that things like this don't happen, such that our model is robust or resilient. So philosophically, there is a difference between robustness and resiliency. I believe robustness means that the model is going to maintain its performance, or the performance is not going to degrade as much under, let's say, some limited disturbances, but at some point it's going to break if the amount of disturbance is going to go up, okay, beyond some threshold. Whereas resiliency typically means that the model, the ability to recover the performance or adapt to a scenario. And naturally, this adaptation in the context of deep learning could require, let's say, retraining or fine-tuning the model at test time. Without that, it is kind of difficult to ask for resiliency. So that's why we are mainly settling for robustness. Nonetheless, the techniques we're going to talk about could be used, let's say, to adapt the model such that we also gain some notion of resiliency. All right. So there are lots of elegant works in the literature when it comes to robustness in the context of machine learning and deep learning. I've selected a few here, and we're going to talk about them briefly, and we're going to tie them back to this perspective of sensitivity. So, so more specifically, robustness in supervised learning can be thought of as sort of reducing the sensitivity of the model with respect to changes or perturbation in the data. Okay, so let's consider this scenario. So I have a simple classification problem, a binary classification problem, and my hope is to learn a classifier that can successfully classify the data into the two classes. Okay. Now let's say that I have the data, I come up with a deep learning model, and I train it, and I find this classifier, which is a nonlinear classifier denoted by this black curve. Okay, and as you can see, it is successful in terms of classifying the data correctly. However, if I introduce some perturbation, a small perturbation, into the training data, the train classifier is not gonna be accurate anymore. Okay, so it's going to make a mistake. For instance, if I perturb this data point slightly, then my classifier, without changing it, is going to basically classify it as a blue class as opposed to orange class. Okay. Same here, right? So if I maybe slightly perturb this data point or that data point, the classifier is going to make a mistake. So therefore, this classifier is not robust with respect to a small changes in the training data. Okay, and naturally you can see here the importance of points that lie near the boundary of the classes. Okay. So the classifier is reliably robust with respect to small changes when it comes to data points that are further away from the boundary, from the class boundary. Okay. Now, the reason that there is a lack of robustness is again the fact that our classifier is sensitive with respect to the changes of data points near the boundary. So one way to reduce the sensitivity is to make sure that there is this let's say this wall around each data point, okay, and crucially around the data points that are near the decision boundary, such that any classifier has to be outside these walls. Okay, so let's say that we ensure this, and then we train a classifier, okay, such that we get this result. As you can see here, the classifier is now further away from the data points near the boundary. In particular, we are introducing some margin, some significant margin, which basically means that if I introduce some small perturbation in the data, such that I perturb points that are near the boundary, like before, then my classifier is not going to make a mistake. Okay. All right. So basically, that's the idea. But there is always a trade-off between like the context that we are introducing and performance, and in this case, the trade-off could be that we are not able to fit the training data as well as we could without introducing this notion of margin. For instance, the classifier that is trained in a robust way could make a mistake here. Okay, so in this case, it is not able to classify this specific example correctly. And this is mainly due to the reason that we are inducing the notion of robustness, and there is naturally a trade-off between robustness and performance. Okay. All right. So our idea, therefore, is to introduce some margin, make sure that the classifier is robust with respect to small changes in the training data. Mathematically, we can model this by introducing this optimization problem, this training problem, where instead of minimizing the average loss over the training data, we basically minimize the following objective. So we minimize the maximum of this loss. In particular, what this is saying is that I take each data point Zi, and then I perturb it with some perturbation vector E. So this could basically mean, like in the example from the previous slide, it could mean that I have an image, and then I perturb it with some noise image E. So it could be like a Gaussian image, for instance. Okay. So I perturb each image, and I want to make sure that I find a model that minimizes the worst case perturbation, where the perturbation has some limited budget. So mathematically, this means that we are imposing the constraint that the norm of the perturbation E is less than or equal to some, let's say, parameter rho, okay, which is a small parameter. In the context of the previous example, it could mean that if we are, for instance, injecting some random noise, the variance of the noise is let's say, around rho square, okay? Or the standard deviation of the noise is rho, okay? So something like 0.01 or something. All right. So therefore, here we are making sure that that our model is robust with respect to a small worst case perturbations in the training data. So if I minimize this loss function, I'll be able to learn a model that is robust against these small perturbations. So in some sense, it's gonna be therefore robust. All right. So how can we solve this problem? Well, there are different approaches in the literature, and one of the most prominent one is the idea of adversarial training and utilizing gradient descent. Okay. So in particular, during the training process, what is suggested to do is to basically perturb the data, okay, according to a solution that we find using gradient descent. Okay. So in particular, let's say that you are considering a specific image ZT. What you're going to do, you're going to perturb it by taking the gradient of the loss evaluated at your current parameter WT, and obviously this image. So this is the gradient of the sample loss with respect to the input, with respect to the features, not parameters, okay? With some step size, let's say eta tilde, and then we make some projection, okay? So first of all, note that, as I mentioned, the gradient is with respect to data, not the parameter. And secondly, this projection operator here aims to ensure that the perturbation is not too large and remains bounded. Okay. So basically, what this is saying is that let's try to estimate that worst case perturbation for each data point by applying gradient methods. Okay. So the approximately worst perturbation is the one that perturbs the image according to the gradient of the loss with respect to that image. Okay, and if that's if that leads to a large perturbation, perhaps we want to apply some projection. For instance, that could mean that we normalize the image such that its norm is bounded by rho. Okay, so that could be like a kind of a projection. Okay. Or we clip the image, for instance. We clip the values of individual like pixels or coordinates, such that overall the perturbation is not too large. Okay. So we find this perturbed image, and then what do we do in training? Well, in training, instead of using the original data, we're going to use this perturbed data to update the model. Okay. So that means that now I'm going to apply basically a gradient-based method, something based on SGD, ADAM, or other methods we talked about in the class, where the stochastic gradient is now evaluated at your current model, as well as the perturbed image. Okay, so we are not using the original data necessarily. Okay. And as I basically mentioned, this method tries to estimate what is the worst case perturbation for each image, for each data point. Okay. Right. So, and this is basically one way to demonstrate it, right? So let's say that I have the original image, which is unperturbed. Let's say this is an image of a dog, and then I find or I try to approximate the worst case perturbation by finding the gradient of the loss with respect to the data, and then I combine the two to find this adversarial image. Now this is something that I'm going to use during the training to make sure that my model is robust with respect to the worst noise that it could see at inference, at test time. All right, so that's one idea then. So we are approximating the max. So remember, our objective was minimize with respect to W, maximize over the perturbation of the loss when I'm perturbing the image. So we were trying to approximate this using gradient methods, okay, iteratively. Okay. So one other idea is as follows. So instead of iteratively solving the maximum, is it possible to actually find a closed form expression for the inner maximization, perhaps under some simplifying assumptions? And then after we do that, we're going to basically go back to the simple case where we are minimizing with respect to W only. So we're minimizing some loss with respect to W only. And then we can apply our favorite gradient-based methods such as SGD or SGD with momentum to find a near optimal solution. Okay. And we can sort of approach this question by trying to write down the Taylor approximation of the loss. Okay, so in particular, let's focus on the first order Taylor approximation of this perturbed loss, if you will, around the original unperturbed image. Okay, so first order Taylor approximation, quite simple. It says that this loss at perturbation is roughly the original unperturbed loss plus the gradient at W and Z. And then here I have the Z plus E minus the point at which I'm writing the Taylor approximation. Note that the gradient here is with respect to Z. Okay, so I'm sort of writing the approximation in the input space, not the parameter space. Okay. Now, so why are we doing this? Basically, remember that we had this maximization problem over E, right? And we wanted to find a closed form expression for that. Now, thanks to writing the first order Taylor approximation, this function is going to be only an affine function of E, which means that the inner maximization problem is actually quite easy to solve, and there exists a closed form expression. So notably, it turns out that this problem is going to have this solution. So again, if I write the first order approximation and then try to find the perturbation that maximizes it, subject to the constraint that the perturbation norm has to be at most rho, the optimal perturbation will be rho times the gradient divided by the norm of the gradient. So this basically is saying that for each parameter and each data point, the maximum perturbation we require to be rho. So that gives us the magnitude of the magnitude perturbation, the maximum perturbation. In addition to the magnitude, we need a direction. The direction is given by the direction of the gradient. Because if I move in this direction, I'm going to basically find the maximum perturbation. Okay, so that's the intuition. Rho dictates what's the maximum magnitude of the perturbation, and this other term here determines the direction for the optimal perturbation. Okay, so how can we proceed from this? Well, after finding this solution, we can plug it back here in this objective, and then after some very basic simplification, we're going to arrive at this training problem, where basically we have a regularized empirical risk minimization. We are minimizing the average loss. This is basically the canonical optimization problem that we deal with in machine learning and deep learning, plus a regularization term, where the regularization term is actually involved. It's not as simple as L2 regularization that we talked about before. It actually is something that depends on the gradient of the loss with respect to the input. Okay, so we are basically penalizing again the sharpness of our loss with respect to the input, and by doing that, we are making sure that we are finding solutions or models that are not sensitive with respect to small perturbations in the input space. Therefore, they will be robust solutions. This is something that could look familiar, and in fact, it is familiar and very similar to sharpness-aware minimization that we talked about before. In sharpness-aware minimization, we were also sort of using the norm of the gradient as a regularization, but the gradient there was with respect to the parameter, not the input data z. Okay, and the idea was that in sharpness-aware minimization, we wanted to be robust with respect to small perturbations in the parameter to ensure that the model has good generalization properties. In this case, we want to make sure that we are robust against small changes in the training data such that the model has good robustness properties. All right. So let's talk about another related approach. And the idea here is that the previous two approaches we talked about rely on finding or trying to estimate the worst case perturbation, but we imposed a condition that the norm of the perturbation is bounded. So in some level, these could be pessimistic solutions. Okay, so it could mean that we gain robustness, but the accuracy of the final model is not going to be good, because practice perhaps is not as bad as we think. So what we can do is to find a workaround, and instead of finding worst case perturbations, we actually utilize the idea of random perturbations instead to induce robustness in our model. Okay, so a simple application of this idea leads to this optimization problem, where we are minimizing again the average loss. However, we take each training data, each sample Zi, and then we perturb it with E. So this is like before. However, instead of having that maximum operator, which we're looking for the worst case perturbation, we have an expectation operator here, which means that our perturbations are random and they come from some distribution P sub E. Okay, and this actually also resembles something we've seen before in the context of zero order SGD and Gaussian smoothing. So this is basically again the convolution of the loss with the PDF of a nice distribution. The difference, however, is that previously we used that idea for gradient estimation, zero order gradient estimation, and we were perturbing the parameter W with the random noise, not the input space, not the input parameters. Sorry, not the input and data point Z. Okay. Now, how can we solve this problem? Let's assume that the noise we are adding is zero mean. Again, it's a very natural assumption. And let's also assume that it has bounded variance or bounded covariance, basically. In particular, I assume that it is like the individual coordinates of this noise vector or perturbation vectors are independent, such that the covariance matrix is some multiple of the identity. Okay. Now, given that, again, our idea, in order to find sort of an equivalent formulation, is to leverage Taylor approximation. However, because the noise is naturally zero mean, we kind of have to write down the second order Taylor approximation to get a meaningful formulation. Okay. So let's again write down the Taylor approximation of the perturbed loss around Z. Okay. So it's the unperturbed loss plus this inner product. Okay. And again, you can see here that if noise is zero mean and I take the expectation with respect to E, this term will be zero. That's why we include the second order term to make sure that we get something meaningful. And the second order term is basically written here. It depends on the Hessian of the loss, not with respect to the parameter W, but with respect to the input sample C. Now, we can actually make a very simple observation that what I've written here is basically a scalar. And a scalar is basically equal to the trace of itself. Okay? And then we can use the property of the trace to make some rearranging and use the fact that trace is a linear operator as well, and also the expectation is a linear operator, such that we can actually arrive to this nice formulation, which again is an example of a regularized empirical risk minimization, where we are minimizing the average loss, like before, our canonical loss, but we are adding a regularization term that with regularization parameter rho plus times the trace of the Hessian. Okay. So in some sense, therefore, this also is capturing sensitivity. It is penalizing the sensitivity of the model with respect to perturbations in the input space. Okay. However, compared to the approach we talked about before, that was using the norm of the gradient to quantify sensitivity, this one is using the trace of the Hessian to quantify sensitivity. Therefore, in some sense, the previous approach was a first order sensitivity-based approach, whereas because it relied on the norm of the gradient, a first order quantity. This approach, however, we can think of it as a second order sensitivity-based approach because it incorporates the trace of the Hessian, which naturally is a second order quantity. Okay. And finally, I want to point out that what we are doing here, again, it regularizes the input curvature. And if you recall from the previous lecture, we talked about memorization and its connection with sensitivity, and also we talked about memorization proxies. One of those proxies was basically the curvature. And the curvature was exactly the trace of the input Hessian, the second order derivative of the loss with respect to the input. So therefore, there is this connection here. So it seems like when we are penalizing the average loss according to this criteria to reduce the sensitivity, we could end up reducing the memorization property of our model as well. So therefore, it seems that memorization and robustness have this intimate connection that if you control one, you may control the other one as well. This is basically an overview of some simple approaches to induce robustness in our models when we make changes in the training data. In the next part of this lecture, we're going to talk about sort of a complementary approach which aims to be robust against changes in the distribution of the data. I'll see you there.